Well, welcome back everyone so far. We're just running the clock at this point before we get started. Kind of an interesting distribution of people present today. We have the full set of everyone who attends in person, and we have Abby being our representative on the Zoom side. Thanks for being here, Abby.
Of course.
Okay, looks like we're ready to begin. Welcome back, everyone. So today's class, we have a couple of objectives really on the table. We're going to return to this if we run out of content to discuss about on exam 2. And chapter 4 is here just in case we didn't have much to do about exam 2. But I did get some questions in a creative way. Thanks to Kate. Kate sent some questions to me through email about things that we'd like to discuss. So I do have a set of questions for us to get going on the review. I have a set of, looks like 2 derivatives, as well as an application problem, which is good because if you look through our notes, over here, section 3.3, I did make a massive hint relative to exam 2, and this is the massive hint right here. Example 3 is a very, very common application problem for our upcoming exam, and something like this will probably come back on the final exam. So we're also going to look into an application problem as well, one that came from section 3.5. It has 2 parts. One part I want to answer in the normal way, but the second part I want to answer in a way that makes it seem like you're doing this sort of problem all over again. So we're going to return to that application problem as well over the course of review. And after we finish those review problems, if there's other questions or problems you'd all want to take a look at, don't hesitate to interject. We'll definitely spend as much time as we feel is necessary. Well, other things to keep in mind about exam 2, we made a lot of comments about it, but as you study it, you want to have this pulled up, available, maybe on another tablet or printed out. But don't bring it to the exam because it will be the last page of the exam. And these are just different versions of sample exams that you could take a look at. Each has its own purpose. This is from the textbook. These are the lecture notes, now worksheets. And this is new additional problems, but those are more challenging. Keep in mind, if you're in version 3, I'm not going to ask the hardest questions in there on a real exam. It's just for the sake of getting extra practice by doing harder problems. Sometimes that is a good strategy on exams. So for our review, I'm going to take the questions that we solved today and put it, it's always hard to tell where it should go. Maybe I'll put it right here. It's going to be titled In-Class Review Exam 2 Review Questions. So brand new file, and let's get started. Oh, well, maybe before we get started, I should address the class. Any questions or comments at the moment about upcoming exam 2 or otherwise? Okay, again, thanks for sending those questions, Kate. That was a very creative way to get some good review questions going. The first problem we're going to do is going to be with these instructions. Differentiate the following function, and 2 functions to take a look at. First one is going to be f of x equals, this one is 2 minus 5x cubed to the power of -2. And the next one we'll look into is g of x, or actually this one was specified as a y equals, and it's ax e to the power -kx. Some of these might look kind of familiar. After we solve these, we'll go to the next question. So let's call this problem 1. I'll leave this more as a reminder. Problem 2, blank right here. And again, if you have other questions, we'll just keep on tacking them on. So don't hesitate to interject. First, let's start off differentiating both of these. This, if you're curious, came from section 3.5, the chain rule section. So both of them are chain rule problems. This one's a little bit more challenging because it's both a product rule and a chain rule all at the same time. So we have to be really mindful of what's going on in that one. But first, let's get going on the first one. F of x is involving an inner function and an outer function. So we can begin analyze by saying power -2, 2 minus 5x cubed are the 2 functions we're considering. That one is the derivative we do second, the inner. Power -2 is derivative we do first. the outer. So that's our typical analysis each time. And because it's a review problem, let's also be even more careful. Let's throw some color coding on here. And now we can say the derivative of f at x is going to be equal to, follow the order of the analysis. If you've gotten the habit of doing this kind of thing, really the whole thing was to make kind of just a thought pattern where everything is methodical so that it's now muscle memory. Just go to where you indicate derivative 1. Power rule says -2, power 1 less. Then I'll put this part in black just to convey this is a feature of the chain rule itself. That's handling derivative number 1. That's tacking on the chain rule portion. And now handling derivative 2. First, we copy in whatever that function is, 2 minus 5x cubed. We copy it in over here as well. And because there's a derivative right here to take, that's what we mean by 2, the derivative we do second. Try not to say second derivative because that makes it sound like f double prime. So that's our first start on getting through the chain rule on this one. Any questions at all, folks, to this step? Okay, and some advice on doing this as a real exam problem. Essentially, anything you put on paper could be worth partial credit. So let's say, for example, maybe we made a big mistake and all of this is wrong. It's right, but let's just imagine that was the case. But if you show this analysis on paper, that is partial credit. You did identify something correct about this being a chain rule and the role that both functions play. So even if everything beyond that point was totally wrong, if this is a 5-point problem, it might be 1 or 2 points partial credit because that's the whole thrust, recognize a chain rule. And if everything we did beyond this, going down below, is totally incorrect, that might be 3 out of 5 points because we correctly started the chain rule. So every step matters, and the more stuff you can put down, it's not just to be helpful to you, it's also to give me just some way to see your thought process and award points by partial credit for the right thought processes. But let's continue to solve this. I believe the power -3 just what it is, so I'm focusing less on the algebra, more on just cranking out the derivative correctly. So I'm going to write -2, 2 minus 5x cubed. Power -3 is totally fine unless we had a specific reason to move it down. And this derivative is still kind of tricky because first, it's the constant rule. That derivative is 0. Then it's the difference rule. We just move from the one term to the next. Now it's the constant multiple rule. -5 survives there. It doesn't go away because it's multiplying a function, whereas 2 vanishes going to 0. Then it's the power rule times 3, x squared. If you put -15x squared here, that's totally fine as well. So altogether, I would probably just end the answer as -2, 2 minus 5x cubed, power -3, minus 15, x squared. And if you're looking at that and you're thinking to yourself, that's a weird spot to end it, I agree with you. It does look weird, but you've got the whole thing here. This is the correct calculus. Any further steps, I consider fully optional. So I want to just convey right here. That's full credit. If you had extra time, or if you just, like me, sometimes have a psychological need to make it look better, you could take those extra steps. If you made a mistake on the algebra going forward, I probably wouldn't mark anything incorrect. I'd probably just circle the correct step and give it a check mark. But this is what you could do if you did want more steps. Take -2 times the -15, so now it's 30x squared. And if you want to correct that exponent, you can drop this whole thing in the denominator, 2 minus 5x cubed, to power 3, and that's a decent stopping point as well. Well, that's the first one down. Any questions at all, folks? Surviving that one there? Okay, now the second question down below, I think this one is a lot more challenging. It's a chain rule, like we said, but that's not the first rule you would use on this one. The major thing that we have to look into right away is it's a product rule problem to start. So let's rewrite it as y equals 8x times e power -kx. I didn't achieve really much here, but by taking this one step, you're kind of organizing in your mind what factor is what in the product rule. I'm going to consider 8x as the first factor, and I'm going to consider e negative kx as the second factor. So if we differentiate this, we can call it dy dx equals, and in the product rule, we're just doing this. Those two terms, those four parentheses, that's the essence of the product rule. The way things get filled in is the other essence. 8x is the first factor on both terms. E negative kx is the second factor on both terms. And this derivative is not bad. That's just an 8. But right here, this is the whole reason this is a challenging problem. That's actually not a very easy derivative. That's in some sense like the whole problem right there. So let's partition this. And do this as a totally separate problem. We'll find out what the result is and plug it back into our overall statement. So let's maybe organize what we were saying here. Product rule. First, in this configuration, that's the first way we would have to differentiate. And then once everything's separated out in this way by product rule, down here, that's the challenge, chain rule, second. Okay, and it's a challenging function. Like you see functions like this in an exam setting, and you really want to make sure you're analyzing it right. A good strategy here is to work by analogy. Simplify the function. Worst thing about this is k feels abstract, right? It's a whole new symbol when we're expecting variables like x. E itself is abstract. We know that that's about 2.71, Euler's number. But if we can take down one level of abstraction by actually putting in something in place of k, this is actually quite a bit of a huge help in seeing how the original derivative should go. So back over here, still a chain rule problem. The inner function is negative 3x. The outer function is this one. And I want to specify it as it's y equals e to the x. Making that little statement right here, y equals e to the x, can help out quite a bit in seeing how the chain rule goes together. So first, you take the derivative of y equals e to the x. That's just itself. Y prime, if y is equal to e to the x, is just e to the x. But it is a chain rule problem, so we know that there's a little bit extra going on. Here's a little bit extra. I'm going to put in a grouping symbol where that x was. Then I'll multiply by the derivative of whatever goes in that grouping symbol. And you know that's exactly what we did over here through the chain rule. We differentiate the outer function first, but the format of that derivative feels so different than the format of this derivative, right? That's just because it was a power function, whereas this is an exponential function. That's the big challenge on this one. Then we take whatever the inner function is. It was that on the last problem dropped in. In our problem, it's negative 3x dropped in here and here. So finally, we just need to finalize the derivative. This is completely fine. It's done. We can drop the parentheses if we like. They were only there for us to see the pattern. We take this derivative. That's just a negative 3. So y prime is negative 3 e to the power negative 3x. So we did this where negative 3 takes on the role of k. Now if we did it again, y equals e to the negative kx, we essentially have an answer. Here's one way to think about that. Let's see, let me get a new color going. That negative 3 that was right here emerges right here. And this is playing the same exact role as negative 3. That means when you go to differentiate, in place of where that negative 3 was, we should get a negative k, and then e to the power negative kx, where there's that negative k emerging in that location there. This is a way to do it. What I've done is I've imagined where -3 is, think of it as a k, and dropped k in those same exact positions. So if that resonates with you, if that makes sense, great way to work by analogy. If this looks crazy to you, no worries, I totally understand. Then you might want to do it in a slightly different way. Let's back off a little bit. And still, we'll use this as an analogy. This time we're going to say that right there is function 2, inner. This one here, face the exponential, is function 1, outer, where y equals e to the x again is what it would originally be, except that we have -kx in that position. So when we go to differentiate, we go y prime equals e to the power times the derivative of that power. So same exact structure here. Grab the -kx, drop it in. And the last thing to do is to take that derivative. -3 is a constant, so when we differentiated, all we got was -3 because power on x is 1. And we just moved -3 to the front. Same exact thing here. Think of that k as -3. It's unspecified really, but it's playing the same exact role. It's a constant. When you differentiate it, because x is to the power 1, all you get is -k. I'm putting it in the front so I don't accidentally say e to the power -kx minus k. It has to be multiplied by -k. And then just drop in the rest. Dropping the parentheses here, popping down e -kx. So what we had here was a -3x. What we have here is a -k. Our answer gave us -3 e -3x. Our answer down here, the one we actually wanted, gave us -k, -kx. So that's the worst derivative. And if you can do this kind of experiment here on the margin, maybe on scratch paper, it really helps drop down the abstraction and allows us to finish off the derivative. Any questions at all, folks, with this result on the right? Kind of a weird problem, right? We spent most of the time on this problem just right here, analyzing the chain rule, and it was a tough one because of k itself. But now the problem is basically complete. I'm going to keep color coding where we took derivative, dropped it everywhere else. Derivative here, just 8. Now copy e power -kx plus 8x. And this is the nasty one. Derivative of that becomes -k, e power -kx. But when you get really good at this, when you feel really practiced, you're probably just going to take that, drop it here, because you know the derivative of e to the power of something is e to the power of that same thing. Then you would differentiate that and just drop it in right there. The idea with this class is we're training our eyes to see and think in those ways. And once you get there, you're probably not going to take much time at all on this kind of problem. But you may take more time out on an exam because we're learning it for the first time. Well, we did it, folks. Those are 2 challenging derivatives. I think this one is more challenging than the original problem up here, even though it looks simpler. Any questions at all getting through either one?
The level that you got to simplify won't matter on this one.
I would say, yeah, it's perfectly fine to leave it just in this format.
I have
Mhm.
on the right side of the plus at 8x, and then e to the -kx in another one, and then just -k.
Gotcha. So if it's formatted, yeah, e -kx here. Only thing we'd have to be careful of is parentheses around that -k.
I have parentheses around the 8x and the e.
So going this way and this way,
So that and
the -k. Gotcha. Yeah, that's what I was going to ask about as well. Yeah, that would be totally fine as an answer as well. The critical parentheses are this one right here by the red dot, because dropping them is saying you're subtracting k as opposed to multiplying by it. If you drop these parentheses here, it would have still, hang on. Yeah, it would still have the same meaning if you drop these parentheses here. I did just double check with my eyes, because that's indicating multiplication, and so is that. But leaving it like this is totally fine as well. It's just a stylistic choice at that point with how you're writing your math. Other questions at the moment? Okay, well, let's go on to the next question then. Let me put it on the next page. This is kind of a challenging document to work on because if you're at the end of the document, you run out of white space, it's actually hard to clean it back. So let's just make sure we have enough here. And finally, for the next question, this was the last question that Kate sent. Question number 2 has an interesting function. Let's define C of t to be equal to 0.0225. Let me try to get those numbers exact. I mean, it's a good problem without the exact numbers, but it would be weird to do a slightly different problem that was asked. E to the power negative 0.0467 t. So that's our function C of t. Interesting side thought. This is called a surge function in pharmacokinetics. Probably misspelling that. Yeah, Google helped me out on the correct spelling. So in pharmacokinetics, seeing the effects of drugs in a system like the human body, this is now called a surge function. Because what we've done here in this experiment is T is the amount of time in, I believe this is minutes, after consumption of 15 milliliters of after consumption of 15 milliliters of ethanol. So looks like it's an experiment seeing what happens with blood alcohol concentration in the bloodstream after consumption of pure ethanol. That sounds like a terrible experiment, but that's what they did. So T is in time, minutes after consumption of that awful shot, and then C of T is the blood alcohol concentration at time. Okay, so that's the whole setup of the problem. And again, it's called a surge function because after doing this, what it's going to look like as a graph is it's pretty low in your bloodstream for a while, but then your liver gets going and it spikes up to a high amount, and your liver starts to metabolize it and it drops down. Let's see if we can plot that just to get a good view of it. So C of t is 0.0225 t e to the power in 0.0467 t. And this is not an easy axis to work with. Let me see if we can get a better view of this function. We want definitely to change the y-axis. It's an exponential, so it's never even negative. And let's go to maybe 1 on that, maybe 0.5. That might be a little bit better. And well, so far this is our surge function. X-axis, let's go to, how about, really it's a t-axis, t for time. And we're going from 0 minutes after consumption to a full hour. And this is what the surge function looks like. Your liver gets cranking out and your blood alcohol concentration is going to maximize for this individual at 21.5 minutes. Everyone's metabolism is different, so this is just an average for the typical human that's healthy, same kind of weight, all that kind of stuff. So blood alcohol concentration, 21.4 minutes, is at that value. That's what the graph is saying. And what we want to do is analyze the rate of change of that function. So it looks like it's for first question, part A, how rapidly was C of t increasing after 9 minutes? This is an honest application problem and pretty similar to the application problem that we were hinting on from section 3.3 as well. So the thing that's really challenging about the way this question is asked is you cannot plug 9 minutes into the original function. That's just your blood alcohol level. It's not the rate at which your blood alcohol level was actually changing. Because it was saying how rapidly is it increasing, that's an indication of what is its rate of change, which means that's a derivative question. Really, it's all that word. Rapid is a speed, which means it's a rate, which means we're talking about the rate of change of blood alcohol in your bloodstream with respect to time. So this is a derivative. Let's use Leibniz notation on this one because we have non-standard variables, C for blood concentration, T for time. The derivative would then be rate of change of blood alcohol concentration, C, with respect to time, T. And now we're differentiating another pretty complicated function. This is a good one. So it's an exponential like the one that we were practicing on just before. Instead of an unspecified value K, it's a little bit more concrete. We have an actual number there, but the numbers are not super friendly. So it has its other kind of noise or abstraction all unique to it. But the very first thing we have to think about is the first differentiation formula we use right out of the gate is product rule again. So product rule first. So here is the pattern of attack on the product rule. This is a good one to be careful on as well because it's just more abstract as an applied problem. So there's my start. Next, we copy in the factors. So 0.0225t will go here and here. Next, the more complicated factor, the exponential function, goes here and here. So two derivatives to take. This is the next one. This one is challenging, but we've seen it a couple ways. So its level of challenge is definitely dropping down. Next step, we can say rate of change of blood alcohol concentration with respect to time, either call it C prime or dC dt, is going to give us this number. T is to power 1, so we just grab the coefficient, 0.0225. Copy this in directly, e to the power negative 0.0467t. More copying, plus 0.0225t. And another challenging derivative, but we're getting better at this. We've given it some good practice already today. This right here is the inner function, derivative 2. And this one right here is the outer function, derivative 1. To ease the complexity of that different looking chain rule, I'm going to call it y equals e to the x. With the parenthesis as a reminder, this is how everything gets put together. And you know what? Let's actually use that two-column system again. Let's do the derivative over here. Well, that looks kind of weird with what I have on paper so far. Maybe that's not going to work out. Let's just do it in stages in line. I didn't really plan ahead too well on this one. So if we're going to do it in line, I've already have this down. Over here, here's where the chain rule is going to start. We get e to the power of something multiplied by the derivative of whatever that thing was. So now inner function goes in the parenthesis above e. And it goes down here as well. So we're just about there. We need to crank out that derivative. It's just going to turn into the constant, negative 0.0467. But then that constant multiplies the positive 0.0225. Let's do that multiplication right here. So from here, actually, let's go, I think it's easier to view if we go left or right. 0.0225 times, result from this derivative is negative 0.0467. Let me double check my numbers. Okay, so we get this number, really small negative, and it's going to go right in front right here. Negative 0.00105 is what I'll round that one to. The challenge is to see if I can remember that number after doing all this copying. Probably not. And I forgot to even put the number right there. So let me double check again. It was negative 0.001505. multiplying this exponential, e to the negative 0.0467t. I think that number down here is kind of hard to visualize, so let me express it. Uh-oh, there's another big problem. I dropped the variable t, didn't I? So we need to throw a t inside there. Let me just sort of squeeze it in this way. Okay, so that's the t that was omitted. Let me drop the highlighting so it doesn't just seem weird. It's highlighted if you come back to these notes. And e to the power negative 0.0467t. Okay, that's now corrected. And what I was trying to say earlier is this number is the result of that times that is where we got that. Does that make sense so far, folks, to this level? Okay, we have a derivative. It's messy, but this is an application. Application problems, especially if we're talking about human metabolism, it's going to give you weird coefficients. That would be really weird if this was a round number. It looked like it wasn't even a realistic to match what's really going on. So next step, because we have to work with this function even more, let's simplify this one. Now this is a time I would actually work pretty hard on trying to get this into a nicer algebraic form. Face the exponential factors out. So let's do that as our first step. E to the power of negative 0.0467t. When we factor that out, I'll leave these as temporary marks just to help us visualize. We're really dividing it out and leaving behind coefficient 0.0225 minus 0.00105 t. So that's our derivative in the most simplified form, and kind of a weird disconnect, right? We've been saying a lot of times the main thrust of the question is the calculus. I'm not as worried about the simplification, but this time I am, because if there's a follow-up question, I don't want to work with the derivative in the messiest way possible. Factor out e to a power, and you only have to enter that in your calculator once. That's actually huge for time and accuracy. So we do simplifications like these when it makes the most sense, and this is one of those times. The question was, how rapidly is blood alcohol concentration increasing after 9 minutes? And so we can say the answer to that question is dc dt evaluated when time equals 9 minutes is going to be this plugged into here and here. So this is a good review on just using the calculator. Don't forget to bring one on the exam. But my standard comment about calculator work on an exam is show what's about to go in the calculator on paper, and you get major partial credit. Depending on the problem, if you put this on paper, e negative 0.0467 by 9, 0.0225 minus 0.00105 times 9. If this is on paper, but what you put in the calculator, maybe you made a simple mistake and it's completely wrong, maybe even the wrong sign in the number that I was expecting, I may not take off any points on that. I would probably just circle this, the check mark, and may say a comment along the lines of, looks like a calculator error, something like that. So as far as partial credit goes on any exam, more relevant to exam 2, this on paper is essentially where all the partial credit comes from. But we still have to answer this, so last step, dc dt t equals 9 minutes is going to be, let me know if you're getting something different in your calculator. So I have e to the power negative 0.0467 times 9. And then that's multiplied by the group, 0.0225 minus 1.00, let me try again, 0.00105 times 9. Let's see if we could look at the whole computation here. So at 9 minutes in, we're right over here. It is increasing, but it's not increasing by much, right? It's at about, for blood alcohol concentration, second coordinate, 0.141, and it goes up to about a 0.177 at its maximum. So we do know it's increasing. We should be getting a positive value, and this is the rate at which it's increasing, 0.00857 units for blood alcohol concentration per minute is the rate at which it's increasing beyond 9 minutes. Really, it surges more right around here at the very start. Makes sense. It's an alcoholic drink. Hits its maximum, and then the liver starts to metabolizing slowly down the line. So let me record that figure. 0.00857 is what I round that to. And what should we say here for blood alcohol concentration? So this was the concentration, maybe called BAC for blood alcohol concentration per minute. I think there's a better unit for that, actually specifying ethanol per maybe a milliliter of human blood, something like that. But that's just the quick and fast units for the information I was given here. I should have probably copied more about the context of the problem down. But any questions at all, folks, on that full process? Okay, so like before, we're trying to connect this problem, like we mentioned before, we're trying to connect this problem to this one right here. This is a problem that we mentioned could potentially, well, I shouldn't say potentially, it's pretty much a guarantee something like this as applied problem will be on exam 2. To really drive that point home, we could throw it on the notes. And also we can do a part B on this problem, which is more similar to that question below. Does that sound all right to folks? A second take on this one? Okay, part A was how rapidly was CFT increasing after 9 minutes? This is how I'd actually write it out as an exam question. Let's call it part B. The question would be, evaluate dC dt at, uh-oh, that's a little bit harder than I remember. I need a bracket. I have all these shortcuts at home, and I forget that typing this out on someone else's computer is not very friendly. There we go. Evaluate this at t equals, let's make this one be 60 minutes. So I would say evaluate. The major feature of the problem is you have to know we're talking about Leibniz notation. That's just a derivative we're going for, and that we're evaluating it at 60 minutes. So it's also kind of a concept to check on Leibniz notation in the first place. Evaluate that and give the correct units. Then give a practical interpretation of its meaning using the context. So this is how I'd probably ask the question A if it's a real exam question for this kind of content. So let's take this away, put it down below. And we've already calculated the derivative. We've simplified it in its most simplified form for our purposes down here. No reason to reinvent the wheel. Let's also inherit that derivative. And say we did the computation. Here it is. Well, not quite. We did the derivative. We still have to do the computation. So we'll go dC dt 1 hour after the consumption of the alcoholic drink, so 60 minutes in, would be equal to e to the power negative 0.0467 times 60, then bracket 0.0225 minus 0.00105 times 60. So this is the new computation. And checking the graph, I know we don't have access to this graph if we're doing it as an exam problem, but still if you're doing it while you're studying, any extra tools that you're working with is pretty helpful. So the thing that's helpful here is at 60 minutes, the blood alcohol concentration is at 0.08. I believe that's still massively illegal to drive at that point, but notice it's going down. So the rate of change then is implying we better get a negative on this one. At 9 minutes, it was increasing. You were getting drunker and drunker essentially. But over here, we're sobering up, but still massively drunk at that point, it looks like. So that gives us some expectations of what should go on. And now in the calculator over here, we'd want to very carefully type in all this. Or in your calculator, call back the last computation. Oftentimes it's something along the lines of maybe an up arrow or second, and an entry button. This is a kind of a basic calculator, so it's hard to do. Because if you call back your last computation, you just make an edit here, put in a 60, another edit here, put in a 60, and that's our new rate of change. It's negative, and it should have been because, again, the curve is decreasing. Derivative has to be negative when the curve is going down. So we get as an output on this, screenshot it just so I can recall the number correctly, negative 0.002, or I'll round that one to 6. I'll give advice on what to round to, and if for some weird reason I forget, do what feels natural. I can't take off points if I don't say what to round to. We also want the correct units, but we would say blood alcohol concentration per minute. So that would be the first part. This is the evaluation, correct units. And this part right here is fantastically tricky. It's one of the reasons I've started getting the habit of putting in a big giveaway that you should expect this problem. It's not easy. And when you go to give the practical interpretation, the thing that is easy just to make a mistake on is to say 0.1718 is the length of the fish when it's 12 years old. That's not true. You'd put the value inside here to get the length of the fish. This quantity is how fast the fish was growing when it was 12 years old. So any interpretation of a derivative is about a rate, some kind of rate of change, either growth, decay, something along those lines. We have something that's negative. So what we should say for our practical interpretation is at 60 minutes after consumption of, this was specifically ethanol, the ethanol. Now we go over here, which is a rate, giving the units is a big help on this, it turns out. The concentration in the blood is decreasing at a rate of 0.00246 in blood alcohol concentration per minute. And notice the curious thing I did here. This might feel a little bit jarring, but when you think about it, it is kind of natural. My answer is negative, but I specified a positive when I went to give the practical interpretation. Anyone see what makes that correct, the positive here, even though it's a stark mismatch? Yeah, well, if you say decreasing, then you're implying the negative in your wording. I'm not going to be really hyper specific. If you said decreasing and put a negative sign in, that really is a double negative. You're actually saying it's increasing, but just something to be aware of. Sometimes writing out these interpretations is a little bit strange if you're thinking about it mathematically. So that's the way this question could be retuned to be similar to how an actual real exam question would be for us. Take a look at how this one went down. The interpretation wasn't the blood alcohol concentration at 60 minutes. It was the rate at which it changed. And same for the problem down below, the throwback from a few weeks ago. Well, any last questions at all, folks? Running through those problems there. Okay, I guess I have a question for the class. Any other further exam review questions you folks would like to touch on? It could be really anything, from a sample exam, lecture notes, maybe a homebrew problem, just a generic open question, homework question, anything like that. That is a really good concept question. Let's spend some time on that one. So the major question here is, in use of the chain rule, how do we determine which function is inner and which function is outer? And that's, again, super important because this establishes the order of doing the chain rule. when we say which function is inner, we're talking about function 2, the inner one. This is just a throwback. Function 2 means this is the derivative we handle second in the chain rule. And when we say which one is the outer, we're talking about function 1, the outer function, the function we do the derivative first in the chain rule. And there's lots of levels to answering this question. First, let's give an abstract answer to this, and then we'll give some more concrete answers. So the chain rule is used when we differentiate a function of the form f of x equals f of g at x. So this is the specific case chain rule pops up. And what this is indicating right here is just ordinary function composition. This is the of when we say f of g. But the thing that's kind of strange about all this is f of g is just the name of the function. It's one symbol, but it's not the formula for calculating the composition f of g of x. So what you probably want to write out next is f of x equals f composed with g at x. So down below is the actual formula for f of g at x. And this is what you probably want to be thinking of a little bit more if you're along the thought processes of what's inner, what's outer. Because this now specifies g of x is the inner function. It's the function that goes inside, literally inside something else in the function composition process. And the f right here, this one is going to be derivative 1, the outer function. So then we say f prime of x, this part right here is the chain rule itself. F prime of x becomes f prime at something multiplied by g prime at x. So this g prime of x is the derivative that we handle second. And the thing that goes inside is just g of x, but it's copied. It's not changed in any way. The derivative is when we chain it by multiplying g prime at x on the next factor. So that's one level of the answer. In the chain rule, this is the process. You determine what's inner, what's outer, by observing the algebraic way the function was composed and picking out the inner function. That gets us started, but what we want to do is make this more concrete now. So if this is the process, the next question we would ask ourselves are, what kind of function compositions do we actually see? We saw a really wild one in section 3.7, derivatives of logarithms. And honestly, that makes the chain rule a little bit confusing because that gave us a whole new pattern. So we'll put down a couple different compositions we'll see relative to exam 2 and see how to exhibit what's inner, what's outer. But any comments so far with what we have on paper here? Okay, so that's the abstract answer, but it has to be there somewhere because it gives us the end all be all for this question. It allows us to handle any composition. And out here are the concrete examples. Let's do a tour of the functions that have come up under the chain rule process. So problem number 1 could be something like this. Y equals, let's make this one be, how about some kind of a power function? Maybe it's 12x cubed minus 7x to the power of, well, literally anything. You know, instead of writing it as a power, we can make this a cube root, a fifth root, anything like that would be essentially dealing with the function of the form y equals x to some power. So this is the first category of chain rules, a power function. but instead of x, there's something else inside of it. Power could be anything. It could look like this. Now the power is really 1/3. Or it could look like this. That's a lot more concrete. That's just x power 5. Or it could look like this. That's like a 7th root, and then the result being cubed. So literally any power whatsoever, it's now a chain rule. And we would say for this one, the thing inside, much like the g of x up here, is the 12x cubed minus 7x. So that's the function inner. And the thing that's out here, the power 3/7, that's the function f, the outer function, which we're kind of indicating right here. So we'll say that this one is derivative 1 outer. So if our function takes on this kind of format, the analysis always kind of goes like that. Well, we might as well differentiate it, right? The question is about what are the examples where this comes up in, but it's weird to just leave it on the table. Should we differentiate it just for the practice? Okay, if I was going to differentiate this, I would probably just write out y prime equals, I would take the 3/7, drop it down. But you're really differentiating this. P comes down, and the new position up here is P minus 1. The power is 3/7. We take 3/7 minus 7/7. So this will be negative 4/7. And here's what I would do next. I would drop 12x cubed minus 7x here. And let me know how you feel about this. We've done the chain rule a lot. So if you've been doing this yourself, it might feel natural. We know the derivative goes here, right? Let's just differentiate it. The derivative of that will be 36x squared. Derivative of that is going to be -7. And then the whole thing is done. Once you do the chain rule a lot and you start to really see the pattern, oftentimes it's just done in one line like that. Does that make sense to folks doing it this way? Okay, this is the first time I've done it this way in class, but honestly, this is the way you probably would read it in a lot of other math books. They often just do the both steps at once. And separating it out in 2 steps is more just so we can see the pattern. But this problem is more about what are the concrete examples for the chain rule. So we did the derivative in kind of a faster way. Here's another example. Actually, without the logarithms, and because we don't have trigonometry as a prerequisite to this class, I don't have a huge amount of examples. That's kind of surprising. So example 2 would be y equals the next big one with chain rule. If I want to make it totally different than this, I can't give you a square root function because that's power 1/2. Same for any root function. We'd have to go to a whole new classification of functions, the exponential ones. Y equals e to the power, let's make it be 7x squared minus 11. That's a chain rule problem, and it's kind of a weird one because, again, it doesn't have the same pattern as the one before. But the category of this kind of function is, it's really a y equals e to the x. Parenthesis around x, just to think of it as function notation. That's where the input would go. That means in this configuration, the inner function is where we made a change on x itself and brought in a whole big function, 7x squared minus 11. That's what makes it an inner function on this one. So we'll call that function 2 inner. And that means, let me fix that. Thought I had a highlighter. That means this one is function 1 outer with the format e to the x. Let me put in a border here. So that's how to tell the difference between the two in this context. Actually, didn't need a border. Let's just move that to the next page. And does that make sense to folks on how to determine inner and outer in this context? Okay, let's do the derivative like before. If you're going to differentiate this and you felt like I've done hundreds of chain rule problems, I know how this goes, this is the short way. Derivative of base e exponential is e to the power of whatever's up there. So I would write a little bit of space in front because I'm anticipating the chain rule, e to the power of 7x squared minus 11. But because that's more than x, we're going to multiply by the derivative of this whole thing. Drops down there. Derivative of this is just going to be a 14x. And the negative 11 would go to a 0. So that's really the whole analysis by chain rule. We do the base c exponential there. We do the derivative of the inner function, 7x squared minus 11, and just tack it on. I like it to the left. It looks a little bit nicer. But if you put it on the right, completely correct as well. So that's the next one. I feel like this one is something you really want to kind of separate in your mind based off of these right here, because the pattern here, we get too used to it, makes this problem way more confusing, right? Whenever it's an exponential. So these are the two concrete examples so far. And again, this is kind of weird because I want to add logarithms to this, but that's not on exam 3, so it doesn't really fit. The only other one I have is y equals something like 7 to the power of x. Really, it's the same as the one above, but if you change the base, it does make it feel like the chain rule is different somehow. So this should be really thought of as a whole new example in that way. What's new about this problem is it is easy to forget this derivative. The derivative with respect to x of 7 to the power of x is 7 to the power of x and a little bit more. Anyone recall what the correcting factor is right here? It's some weird constant. And again, no worries if you're not sure, because it is a weird derivative. It came up in section 3.5 on the chain rule, and we did use it there. It's in the homework, but it still feels brand new. So let's imagine this is an exam question, which we do at this point. We'll flip in our exam to the exam 2 formula sheet, start looking at guidance. Here's where derivative information starts coming into play. And that is actually what we needed. This is the derivative of a generic base exponential. It is b to the x. We wrote 7 to the x in our problem, but you multiply by the natural logarithm of the base. That's the so-called corrective factor we were mentioning. This is a good one to throw into our notes, just as a reminder. Let's drop it in maybe right here. Oh, that broke everything. How about we'll put it in below. So with that guidance right there, we could take this base 7, multiply by the natural logarithm of that base. So that's the essence of this differentiation formula. It's much like e to the x, but it involves one extra factor. So that's if it's y equals 7 to the x, but let me think about that. That's not a chain rule at all, right? That's just 7 to the x. What if it was 7 to the 2x minus 5? Now it's a chain rule because it became a function composition. Not just 7 to the x is a whole function itself, 2x minus 5. So like in the last problem, we would call this one the inner function, the one we do second, because it's inside the x right over here. We drop something additional in that position. The function itself, y equals 7 to the x, base 7 exponential function is the outer. And again, we write the functions this way. Sometimes it's not a bad idea to put a little parenthesis there to remind you it's true function notation, just like saying f of x or log base b of x could also be written as log base b of the input x, also forcing function notation and so on. So if that's a helpful change of view to make, I'd say do it because the chain rule is tricky and this is really indicating what goes where to set the pattern. Let's do this one without a shortcut. It's actually pretty complicated because of the extra noise that we have to navigate through. Let's write out an ordinary y prime or dy dx is synonymous is going to be, following the guidance, differentiate the outer function. That'll be 7 to the power of some input. With, Here's the easy part to forget, natural log 7 thrown in as well. I'm putting that part in yellow just to highlight the tricky part of using this theorem below. Then, because it's a chain rule, we multiply by the derivative of something. So this is the pattern. We took the derivative, here it is. In place of this x, we're putting something else, 2x minus 5. And because it's not just x, we differentiate it by it as well. So it goes in both of those positions, and now we're ready to finalize this one. This is the major logical leap, though, from the original function to the first step in the chain rule. Any questions at all, folks, getting to this spot? Something like this could be on the test, but not necessarily a guarantee. Definitely something to watch out for, because if it's on the formula sheet, then it was my way of saying it may be on the exam. There's a possibility it's going to be somewhere. Maybe not a big problem, maybe tacked on to something like y equals x cubed plus 5x plus 5 to the x could come up. Other questions so far? No, now that we mentioned that, let's write that down here. Y equals x cubed plus 5x minus 5 to the x plus e cubed. Let's do that one next, because that, is still a challenging problem based on what we've said before. And then back up here, finalizing this problem is just one more derivative. This derivative is 2. So all I want to do is put a 2 out in front. Personally, I'd format my answer as y equals 2, which came from over here. I can color code that to convey it better. Let me try again. So here's the 2 from that derivative. Then I would put the next constant in front, natural log 7. Then I would write out the exponential function. I would probably personally drop the parentheses. They're just there for us to see the pattern in the chain rule. And that's the whole answer with the last derivative taken. So these are the 3 different contexts where a chain rule can come up. And this would be the way I would analyze what's inner, what's outer. It all just depends on the format of the function. That's what makes it kind of a complicated question to answer, but a very worthy one to spend some time on. Thanks for asking about it. Other questions at the moment, folks? Okay, I guess this is my question to have for the review. I think it's a good one because in exam 2, when we are going to doing properties of differentiation formulas, you should expect a lot of little problems like these, just like you're seeing in the notes in sections 3.3, 3.4, 3.5. So doing this derivative, this is really all you have to say. dy dx equals, differentiate x cubed. This is a normal function, so this is the fun one. It would be 3x squared. And you know what? Let's make this a little bit worse. Sorry for folks in pen, but it might be a good idea to do 5 to the power negative 3. Because when there's a negative 3 power, it can sometimes throw us off on the ordinary patterns. So sorry for this change. The change is that power negative 3 right there. If we differentiate this next term, we'll get a negative 15 coefficient. But the easy mistake to make on exam, usually it's just because of the extra pressure, it's timed, all that kind of stuff. It doesn't become negative 2, it becomes negative 4. So it always goes down by 1. And that's really kind of easy to forget. It's just a directionality thing. This one's not nice though. Any volunteers for derivative negative 5x?
Natural log 5.
Good call, absolutely. Kind of like that.
Yeah, and then just the plus, same thing.
Yeah, that would be totally fine for expressing it this way. Actually, let's leave it on paper that way, just to convey. If you went that way, you might have wrote it in kind of like this. Negative outside, 5 to the x, natural log 5. The only change was I dropped a parenthesis around there, so it's now a whole bunch of parentheses altogether. And this one's even worse in trickiness. What's the derivative of e cubed? Any volunteers for that one? Turns out this one does change. It's like one of those weird, awful concept check questions. Absolutely, good call. This one is constant. Let me say what you said verbatim. Constant since it doesn't have an x. So that just vanishes, disappears. Technically, we'd say the derivative of it is 0. D by dx of e cubed, or just e cubed prime if you prefer, is 0. So this one, we wouldn't have to write in anything additional on that. Those are always weird, so watch out for, even this could come up. D by dx of natural log 7. This one's come up in our notes as well, even before we got into the logarithm section 3.7, because it's also constant. What makes it a really nasty problem is what everyone's expecting when they see it is d by dx of e to the x or something like that does give us e to the x, d by dx of e to the 3x. That would give us e to the 3x, and then we would differentiate 3x through the chain rule, drop a 3 down. But this one is designed to check the concept. Missing an x means it's literally constant, and now we don't write in anything. It's vanished. Well, any questions at all, folks, on that last one? Exactly, yeah. Now we're dealing with more of an exponent law where e power 0 is 1, as you said. We would also say a to the power of 0 is 1, provided a is not 0. Here's one thing that's really, really weird. 0 to power 0, undefined. And the reasons for why it's undefined are really varied. It turns out the best explanation is in calculus 3. That's bizarre in a certain sense. You know, I'm kind of curious. What does Desmos say about 0 power 0? 1. That's kind of interesting. A lot of programs would say undefined. Maybe one other check on this. Sorry for the sidetrack thought, but this is important exponent laws. On this calculator, 0 power 0, domain error, undefined. This calculator is more about calculus, it turns out. And this is a standard assumption until we're told otherwise by convention to treat it as 1. And that's what Desmos is doing. They're saying by convention it equals 1. But there is still really good reasons it should be undefined. I think the calculator has the better take on this, the TID3. Well, any other questions at the moment, folks, about reviewing exam 2? Okay, well, this has been a really productive review day, I'd say. Again, thanks for the folks for posing questions in class live. Thanks again for Kate as well for sending in questions by email. I'll give that as a reminder next time when we're reviewing ahead of exam 3 and the final exam. Happy to take your questions by email as well. And the reason that's such a brilliant strategy is oftentimes the question in your mind feels really important in the moment, and then if you wait to class, you forget about it. So if you just send out your question the moment it strikes you, that's the best time. With what we have left in class, looks like we're down to the last 6 minutes and some change. I don't think I have enough time to really go forward in the notes. So I think this will be a good stopping point for us today. Unless there's any last additional final burning questions that we can address. Okay, well, have a great weekend, folks, and great afternoon. When you're studying on exam 2, this is just a generic comment I mention about every exam. If you're studying on exam 2 over the weekend, don't hesitate to email. I'm pretty busy too over these weekends when we go into an exam week, so I'll be quite a bit available. But have a great weekend, folks. I'll see you all on Tuesday's class. Or Tuesday's exam. So if you're on the fully online section, we won't have a Zoom class. It'll be all about the exam. Yep, take care.
Question for you about last week's design assignment.
Yeah.
So I have the work with me, but I was doing like all the problems and I'm pretty sure I simplified them to their simplest forms.
Yeah.
And I put them in there, but it was saying they were wrong.
Mhm.
And so I was just wondering.
Do you remember which section it was in?
It was the one that was due last week.
Gotcha.